So the book has chapters on the components of the climate model, mostly atmosphere, ocean, and land. One could think of humans as now a part of the climate system as well, in what is called external forcing. When we say forcing in a climate model, we talk about anything that perturbs the radiation balance at the top of the atmosphere and hence results in climate change. And typically the external forcings are volcanoes, which take out stuff that is underground and throws it into the atmosphere and changes radiation balance, and of course orbital changes and solar activity, which change the energy balance as well. Okay, so in that sense, many Earth system models want to include a human component, but then there is another class of models called integrated assessment models, which are focused much more on macroeconomics, socioeconomical choices, technology, energy, agriculture, food, transportation, and how they interact with climate, or how climate change affects these spheres, and how the policy choices and technologies then feed back to climate and so on, or how you strategize mitigation and adaptation. So integrated assessment models simplify the climate part and focus on the socioeconomic sectors and humans, whereas Earth system models simplify the human influence and focus on the physical and biogeochemical climate. Okay, so integrated assessment model is mentioned in this book several times. I'm not going to say more about it. I have podcasts on it elsewhere that you can look up. So I'm going to, and the book in each chapter provides some details or on descriptive details on how atmospheric model is constructed and what are the challenges it faces, difference between weather and climate, and how it differs from the ocean model, and what are the challenges of an ocean model, how it is constructed, and what role ocean plays in the climate, and similarly for land models. I'm going to just club some of those points into this podcast so that when we go into the component models, we will not talk so much about these details there. This gives you a good context before you listen to those model components. Okay, so let's start with a simple schematic of the history of how models have evolved. We will look at this again a little bit later when we couple the models back together. So in the 60s, GFDL was a hotspot with Sukiro Manabe, who just won the Nobel Prize, and Kirk Bryan, who was working closely with, they were collaborating together closely, and Suki was focusing on coupled models, atmosphere, how to keep the coupled system coherent by using techniques called flux correction, because the models don't balance energy properly, and that leads to biases and growing temperature trends and so on. So he had found a way of fixing water by adding water here, removing there, by adding energy here and removing it there. Now people don't like doing that, but Sukiro is very much still arguing that they should be done because the model biases still exist. So it may be an option that must be considered. Okay, and Kirk Bryan developed an ocean model, which became eventually the modular ocean model, which is still maintained and served to the community by GFDL. Now it's called GOLD, I think, Global Ocean Layer Dynamics, where they are combining the advantages of a XYZ coordinate with layers, because ocean is strongly stratified. Often it's advantageous to use isopycnals, or constant density layers, as a coordinate. Similar things exist in the atmosphere to take care of the orography and so on. That's called a sigma coordinate, but let's not go into those details here. So atmosphere, land surface, and vegetation, simplified vegetation models evolved during the 60s and 70s, and ocean model evolved along the way. Coupling happened, so coupled climate models became quite ubiquitous in the 80s. Sea ice was developed first as a one-dimensional model and then coupled to the ocean. Typically, things are always developed separately. The land model, the planetary boundary layer model, a convection model, land model, vegetation model, and then slowly they're coupled together. So coupling happens here. You can see the diversity growing here. In the 90s, the role of aerosols became very well known and considered important, including things like acid rain, for example. So sulfate aerosols appeared first, and you can see then interactive vegetation coming along, so-called dynamic vegetation, which responds to temperature change, precipitation change, vapor pressure deficit change, and so on. Dust, spray, carbon aerosols got added. Carbon cycle and other biogeochemical cycles came along in the last 15, 20, 30 years. Ice sheet models became much more common in just about the last decade. So earlier IPCC assessments were done without the ice sheet models. Most of them had sea ice. Some of them had only physical climate. Many had sulfate aerosols, carbon cycle, and so on. There are other details about whether the models included the feedback from carbon cycle to climate and so on. Now marine ecosystems are being run as a part of the global Earth system models, and the transition from climate models to Earth system models basically means you have carbon cycle, and often also means you have ecosystems like vegetation dynamics and marine ecosystems, even though a land model typically must include some form of vegetation representation because it's an important part of the energy exchange between the land and the atmosphere. So upper atmosphere, it's become much more known now that stratosphere troposphere interactions are very important, and then atmospheric chemistry, and as we have already said, adding chemistry and ecosystems adds massive computational costs, so often various choices are made in making long simulations about turning them on and off and so on and so forth. But the feedbacks between chemistry and climate, ecosystems and climate, ice sheets and climate, carbon cycle and climate, aerosols, direct and indirect effects and so on are now very well known. So many of them are also studied in regional contexts, in process studies, rather than running the full global model all the time. Okay, so sorry, here it should be model mechanisms. Let me correct that right now. Model mechanics, sorry, that's the title used by the book, so I'll use the same. So next three chapters, are on the components, so atmospheric model, ocean model, and land model. We will have a podcast on each, very brief discussion since this is just a introduction to models. So atmospheric models are obviously taking the energy coming in at the top, absorbing whatever is absorbed within the system, and then it needs a bottom boundary condition because it's forced from the bottom, from the land side and from the ocean side. So typically when atmosphere only models are run, the sea surface temperatures are prescribed in some form, either fixed to a climatology or the seasonal cycle, or interannually varying, or a climatology plus an anomaly, just say in the El Nino region or Indian Ocean dipole region, and so on and so forth, depending on what it is that you are looking for. So just running the and similarly on land, some prescription happens, but often land interacts with the atmosphere in these cases, not with the vegetation and everything, but land has low heat capacity, higher than the atmosphere, but low compared to the ocean. It reacts quite fast to changes in the atmospheric dynamics and thermodynamics. So when you run an atmosphere model, typically you need the land to be interactive. Okay, so atmospheric models then have to worry a lot about energy balance, the radiation, because atmosphere has low heat capacity, can move fast. Small errors in energy balance can make a big difference in dynamics and thermodynamics. The scales, of course, go from frontal boundaries, cyclones, cold waves, heat, cold fronts, warm fronts, and large-scale systems like trade winds, Hadley cell, and in the middle you have cyclones and so on. And they have to worry about the feedbacks about how land changes like urbanization, agriculture, deforestation affect the atmosphere, and how cloud changes affect the atmosphere, how warming and cooling affects the humidity content, and the feedback through greenhouse gas effects, and of course the lapse rate feedback as well that we talked about elsewhere. And atmospheric models are run typically most commonly for weather forecasts, because weather is what is called an initial value problem. Because you're only running for a few days, the changes in the ocean are slow, so ocean can be prescribed and some sort of a land interaction happens. So weather forecasts can be done with just atmosphere models in this sense, which means computational cost is lower, which means much higher resolution of an atmospheric model can be used as opposed to a full Earth system model where running the ocean, the atmosphere, and the land together becomes very expensive. Initial value means it is integrated by starting at one point, let's say 6 a.m. of every day, and then run every 6 hours, let's say at 12 p.m., 6 p.m., 12 a.m., and so on. I'm just using it as an example. So all the quantities at every grid point on Earth, if it is a global atmosphere model, or in a regional model, you will need to prescribe boundary conditions, as we will see later on. So winds, temperature, humidity, and aerosols, and various land, ocean, etc. have to be prescribed. Whereas climate is called a boundary value problem, which means once you want to go beyond a few days, you remember probably from somewhere that weather becomes chaotic after a few days because the system is very nonlinear, the famous Ed Lorenz work on chaos. So initial value problem goes chaotic after a few days. In the tropics, weather forecast is very limited, just a few days, because convection, very fast systems happen. In the mid-latitudes, where things lumber along at large scales for many days, weather forecast skill can be out to 5, 7, 10 days. And chaos, the errors in the model forecast become too large after that, but there is something called predictability of the second kind, where the slow-moving ocean, slow warming, slow heating of the ocean begins to control the evolution of the coupled system, so we can still make forecasts for many seasons, many months, and sometimes even a year for things like El Nino, monsoon, and other things as examples. So that's the difference between weather and climate. There, as it is said, weather is what you climate is what you expect, and weather is what you get. So in summer you expect a warm temperature, but on a particular day it may be cooler because of some front coming along, and so on and so forth. And applications include various weather forecasts have applications for the transportation, aviation, agriculture, and heat waves, air quality, and so on and so forth. Ocean models, ocean is forced from the top. The forcing from the bottom or interior is not very significant, other than the mixing caused by sloshing of the tides, and the tides hitting mountains in the ocean and creating mixing. Ocean has very high heat capacity and provides all the memory for the climate because of, as we said in the second, the predictability of the second kind. Moves slowly, provides, so takes up more than 90% of the additional energy and 25% of the CO2 that's being emitted. So those are the kind of issues, and the carbon cycle becomes important as well. Sea ice is important because of the ice albedo feedback, and of course ocean is an important part of climate change problem, because you cannot really do climate change with just an atmospheric model. Ocean keeps 90% of the energy and releases at various slow timescales and modulates climate change, and it stores a lot of that heat and carbon as well. So land models, the heterogeneity is very important. You look out the window, you see all kinds of vegetation, buildings, water, maybe snow, ice, mountains, and so on. So that's very important. And humans live on land mostly, and human impacts are very critical. Hydrology, so precipitation, water. Water is very critical for life, for agriculture, for existence, and ecosystem dynamics like vegetation. Hence, carbon, nitrogen, and phosphorus cycles, because of agriculture. These are very important, and how large the perturbations by humans are, and how those cycles then interact with climate. Snow and glaciers, very critical for albedo feedbacks, as well as sea level rise problem and so on, and even pushing the land down if glaciers get very big. Integrated assessment models come in here again in terms of future projections and the pathways we choose for how carbon will evolve, how humans will evolve, how population increase, socioeconomic sustainability options, technology, renewable energy, and so on. So integrated assessment models try to do all that. Coupling atmosphere, ocean, land models, and as I said, some now begin to include humans in some form, at least in terms of increasing greenhouse gases, for example. Complexity increases because everything is responding to everything, everything is feeding back to everything, and scales are very different. Atmosphere responds very quickly, and land responds a little bit slower, but ocean responds much slower, and there are all these time scales, fast, rapid processes and slow processes, so multitude of spatial and temporal scales. Interest in information is from local scales to regional scales to global governance issues like mitigation of global CO2 levels, net zero, decarbonization, and so on. And there are lots of coupled feedbacks like the ice albedo feedbacks, water vapor feedbacks, cloud feedbacks, and there are things like natural variability and how they are modulated by anthropogenic forcing. So we'll look at some examples of natural variability when we look at coupled models. Okay, so let me leave that there and then come back and start with the atmospheric component of the model. I use this podcast just to orient you towards the atmosphere model, land model, and ocean model, and their coupling. And I wanted to club the various issues of each model together in one podcast, and then just focus on the other issues of modeling and simulations of each component in the coming podcasts. Okay.